So in this video, we're going to talk about local mins and maxes in 3 dimensions. And if we go back to Calc 1, remember that there were kind of 3 options if the derivative was equal to 0. So if you had this slope of 0, then there were 3 different things that could happen. You could either have a max. So in this scenario, here's that slope, the point where the slope is 0. It's a local max. It is concave down, and so the second derivative is negative. You could have a min, there's that slope of 0. If you have a min, then it's concave up, and the second derivative is positive. Remember, this is called the second derivative test. And then if, and it was also possible to have neither a max or a min, but still have a 0 point or a 0 slope where you have an inflection point. And if that happens, then the second derivative is 0. So we have this second derivative test for local mins and maxes, and there is an equivalent in 3 dimensions. Now below this, I have 3 other pictures of mins, maxes, and neither in 3 dimensions. So this first picture here, here's a max in 3 dimensions. Here's where you would have a local min in 3 dimensions. And then here's a picture, this last picture is where you would have neither. And notice that there are there's 2 parabolas on there. One of them, actually let me pick a different color here. This parabola here is where we would have a min, but there is another parabola here, and along this parabola it's a max. So it's neither a min or a max. It's kind of that similar situation as an inflection point, but in 3 dimensions. All right, so let me give you the kind of how to find these mins and maxes and the second derivative test. So this is kind of some rules on how to find local mins and maxes. The first thing that you want to do is find the partial with respect to x and set it equal to 0, and the partial with respect to y and set that equal to 0, and then solve for the x, y points that give you that both of these partials are 0. So this is the equivalent of finding that 0 slope, but we have to find a 0 slope in both directions in order for it to be a local min or a local max. All right, so these are called the critical points now, same as in Calc 1. So we've got critical points. Then the second thing you're going to do, and this is part of finding this is kind of the second derivative test. So what you're going to do, you're going to find, we're going to call this D. It's going to be a determinant. I'll tell you kind of how to find a determinant. This is maybe the first time you've seen it. Of the second partial with respect to x in the upper left-hand corner. The second partial with x first and then y in the upper right, the second partial with y first and then x in the lower left, and the second partial with both y's in the lower right. I remember this by remembering we're going to do x's first in the first row and y's first in the second row, and then x in the first column, y in the second column second. This is also on your equation sheet. All right, so now here's how you find this determinant. It's kind of like, it's like taking a cross product. You multiply down, so that is f sub x times f sub y, and then you subtract when you multiply up. So same as finding that cross product. So this is going to be sorry, I just ran into my subtraction sign. So minus the function. Now, remember the continuity of these partial derivatives, and that when we're dealing with continuous functions, those partial derivatives are the same. So I'm just going to take one of them and square it because they'll be the same thing, that lower left and upper right. All right, so that's our determinant. Okay, so now here is kind of the rules of the test. So if D is greater than 0 and the second derivative with respect to x is greater than 0, then it's a local max. If D is greater than 0 and the second partial with respect to x is less than 0, then it's a local min. We could do the same thing. Instead of x's here, we could use the double with respect to y. Essentially, we're just taking a second derivative to find concavity in one direction. But if this determinant is greater than 0, it does say that we're not going to have that sort of saddle point, that inflection point. It will be a max or a min. And then this second derivative just tells us concavity, whether it's positive and it's a max or negative and a min. And then if D is less than 0, then it's a saddle point. The saddle point is the equivalent of that inflection point. And if D equals 0, then it tells you nothing. There's no conclusion. So in our problems, if you get a D equals 0, then something is not quite right. You probably made some sort of an algebra mistake. All right, let's do one example. So let's find the local mins, maxes, and saddle points. Local min, max, and saddle points for the function if f of xy is equal to 2x cubed plus xy squared plus 5x squared plus y squared. All right, now remember step 1 is that we had to take a partial with respect to x and a partial with respect to y, and then we're going to set those equal to 0. So the partial with respect to x, there's an x, so it's going to be 6x squared, and then I'm looking at the next term. Y is just a number, so that's just going to stay there, a y squared. Next one has an x, so 5 times 2 is 10x, and y is just a number, derivative of a number is 0. So there's the partial with respect to x. Now the partial with respect to y, the first term has just an x, so that's going to be a constant, which will go to 0. The second term has a y in it, so let's bring that 2 down in front. X stays as x, and then we'll have y to the first power. That third term has x's, that's going to go to 0. And the fourth one, we'll take the derivative of that and get 2y. All right, so we're going to set these both equal to 0. Now you may have to review a little bit of algebra on this part, because these can be a little bit kind of interesting to solve. But what I do is I take the simplest equation. So I'm going to choose this one with y's because it's a little bit simpler than the other one. So now if I look at that equation, I could factor a y out of that. And if I factor out a y, I'm left with 2x plus 2 equals 0. So now I look at each one of the factors of this and set it equal to 0. So when I do that, I'm going to set y equal to 0. So I'm going to set y equal to 0. And then separately from that, I'm going to set 2x plus 2 equal to 0. So that would be x would have to equal -1. So when I set 2x plus 2 equal to 0, I get x equal to -1. All right, so now what I do is I only have used one equation so far. I'm going to take those numbers and plug it into the equation that I haven't used. So I'm taking y equals 0 and I'm going to plug it into the equation that I haven't used. Y equals 0 into this equation I haven't used. When I do that, I get 6x squared plus 0 plus 10x, oops, I'm running out of room here, equal to 0. I can factor an x out of that. And actually, I could even factor a 2x out of that. And then I'd be left with 3x plus 5 equals 0. And this gives me now two values of x for each factor. X equals 0 and x equals negative 5/3. So I now have two different equilibrium points from this. I'm going to write them kind of down lower on the page. I'm going to leave some room to find that determinant. But here are my equilibrium points. So far, I have 0, 0, and 0, negative, nope, not 0, negative 5/3, other way around. X is 5/3, or negative 5/3. And y was 0. Okay, so there's two equilibrium points. Now I've got this x equals negative 1 still. I still need to take it and plug it into that equation that we haven't looked at yet. So negative 1 squared is 1, so that's a 6, plus y squared minus 10, y squared minus 10 is equal to 0. So that gives me y squared minus 4. I'm going to move that 4 to the other side, and we get y equals plus or minus 2. Now that's two values of y that go with x equals negative 1. Notice I draw this line in here so that I'm not mixing up that y equals 2 goes with 0. If you plugged those back in here, they wouldn't work. So I keep it separate. This gives me two more equilibrium points. X equals negative 1 and y equals positive 2. X equals negative 1 and y equals negative 2. All right, so there's the first step, finding those equilibrium points. Now we need to find this determinant. In the upper left-hand corner, we're going to take the second partial with respect to x. Let's see, do I have enough room to write out what, well, it's okay. Second partial with respect to x right now in that upper left-hand corner. So I'm going to look at my first partial with respect to x and take a derivative with respect to x again. So I get 12x plus 10. Then in the upper right, I'm going to take that same equation that I just looked at, but take the partial with respect to y. So that would just be a 2y. Now in the lower left, I'm going to take the partial of this partial with respect to y. I'm going to do that with respect to x first. So if I do that, I'm just looking at this guy. So that would be 2y. And then I take the partial with respect to y. So that would be 2x, 2x plus 2. I had to think about that one. It gets confusing when you switch variables back and forth. Okay. So there's all my partials. So now I'm going to treat this like I would kind of treat part of a cross product. Multiply down, so 12x plus 10 times 2x plus 2. Sorry, let me separate all this out. And then minus 4y squared. I multiplied the other diagonal and subtracted it. All right, so there's D. And then we also need, for this next part, the second partial with respect to x. We already found that. It's the upper left. It's 12x plus 10. Okay, so now we need to, for each one of these, figure out whether D is positive or negative. The second partial, we might need some of that, and then let's make a conclusion about it. A conclusion, is it a local min, a local max, or an a saddle point? Okay, so let's plug in 0, 0. I'm plugging in 0, 0 into this determinant. So when I plug in 0, 0, that takes away that whole y term. And then I'm going to have a positive value here because I'm going to have 10, and a positive value here because I'm going to have 2. So that determinant is positive. If you want to find the number, it's 20, right? If you multiply those together, but that's not a necessity. But it's positive. So if it's positive, we actually have to look at that second derivative. And if we plug in 0 into that second derivative, we get 10. So that's positive. Positive, so I think of that as a smiley face. And so that is a local min. So at 0, 0, we'll have a local min. All right, we've got 3 more to do. Same thing. We're going to take negative 5/3 and plug it into negative 5/3, 0, plug it into this equation. Now, once again, y is 0, so it takes away that second part. And then for the first part, if I plug in negative 5/3 into this first equation, let's see, if that's negative, it's 5/3 is bigger than negative 1, that's for sure. So this guy's going to be negative, and so will this one. So negative times negative is a positive. So now I have to look at that second derivative, and we've already determined it was negative just by looking at that first part. So this one is a local max. So now at negative 1, 2. So now for this one, the y squared, so now we have 2 squared. So 2 squared is 4, 4 times 4, we're going to have to subtract 16. And then if we look at the first part, so x was negative 1. So negative 1 gives me negative 2 in that first and that second partial. And then, oh, it's going to give me 0 right there. Okay, so we get negative 16. So negative for that determinant. It means that we don't even need to find that second partial with respect to x because it's automatically a saddle point. The next and last one, that negative 1 gave us a 0 right here. And then if we look at this next part, if we square y, multiply it again, we once again get negative 16. That's negative and gives us a saddle point. Okay, so the next video we'll talk about absolute maxes and mins.